Welcome, everyone. I am absolutely stoked to guide you through this explainer of a truly brilliant data structures and algorithms problem. We're pulling this directly from the incredibly comprehensive Striver's A to Z course, which, frankly, one of the best guides out there for mastering DSA. Today, we are looking at a total classic, rearranging array elements by sign. It sounds pretty simple on the surface, but trust me, it has layers. We're going to explore two different varieties of this exact same problem, and we'll see firsthand how just a tiny change in the rules can force us to completely rethink our entire approach.
Here is our roadmap for today. We'll hit the core problem, look at our safety net, which is the brute force approach, then jump right into the one-pass optimization. After that, we tackle the unequal elements twist, pivot our strategy, and finally wrap it all up with space and time complexity. Let's just dive right in.
All right, section 1, the core problem. So in this first variety of the problem, we get a really nice guarantee. We are handed an array with an exactly equal number of positive and negative elements. That means if the total length is n, you absolutely know half are positive and half are negative. Our job is to rearrange these elements so they alternate perfectly, positive, negative, positive, negative. But there is a massive catch. The absolute crucial point here is this concept of relative order. As we're alternating these numbers, we literally cannot mix up their original sequence. If you're scanning the original array from left to right, and the positive numbers show up as 3, then 1, then 2, well, in your final alternating array, those positive numbers have to appear in that exact same order, 3, 1, 2. And the exact same strict rule applies to the negative numbers.
Let's look at an example that really hits the nail on the head. On the left side, we've got our original completely mixed up array, 3, 1, 2, -2, -5, -4. The positives are 3, 1, 2. The negatives are -2, -5, -4. When we rearrange them to alternate perfectly, we start with a positive, 3. Then our first negative, -2. Then our second positive, 1. And our second negative, -5. Notice how they alternate perfectly, but more importantly, if you just read the positive numbers in that finished product, they are still 3, 1, 2. The relative order is completely untouched.
Moving on to section 2, the safety net, or as we all know it, brute force.
Look, when an interviewer throws this at you, the very first solution that pops into your head is usually your safety net. Don't overthink it right out of the gate, right? We're going to start with his brute force approach because it's totally valid and highly logical. Step 1. You just grab 2 empty buckets, one for positives, one for negatives. You walk through the whole array once. If it's positive, toss it in the positive bucket. Negative, toss it in the negative bucket. Because you're reading left to right, boom, relative order is naturally saved. Now for step 2, we just stitch them back together. Think about it. Positives always sit at index 0, 2, 4, the even seats. Negatives sit at 1, 3, 5, the odd seats. So we just loop through our separated lists and place the positives at index 2 times I and the negatives at index 2 times I plus 1. Easy.
Okay, section 3, the one-pass optimization.
Boom! You proved you can solve it, you got the right answer. But now the interviewer leans in and asks the classic follow-up. Can you do this without the extra iteration passes? We did one pass to separate them and another completely separate pass to stitch them back together. Can we reduce this down to just one single pass? We know we still need a new array to hand back our final answer, so we can't completely eliminate extra space, but we definitely want to shave down the time. To do this, we've got to figure out how to drop elements directly into their final permanent seats the very second we look at them in the original array.
Let's see how this optimal logic comes together. Instead of collecting elements into separate buckets first, we just prep our final answer array and set up 2 pointers. We put a pos index starting at 0 because the very first positive goes to index 0. We set a neg index at 1 because the first negative goes to index 1. Now we literally just stroll through the original array one time. If we see a positive number, we drop it straight into the pos index seat, and then we just bump that pointer up by 2 spaces. Why 2? Because the next positive seat is exactly 2 spots down the line. If we see a negative number, we drop it at neg index and bump neg index up by 2. One single pass, perfectly arranged, absolutely optimal.
But wait, section 4, the unequal elements twist.
You're feeling super confident, the interviewer is smiling, and you think you've got this in the bag. Then they throw a massive curveball. Welcome to variety number 2. What if the array does not have an equal amount of positives and negatives? The whole game just changed. Positives are no longer guaranteed to equal negatives. You might get 4 positives and only 2 negatives. The new rule is to alternate positive and negative elements for as long as humanly possible. And once we run out of the sign that has fewer elements, we just take all the leftover numbers and casually tack them straight onto the end of the array, and of course, we absolutely cannot alter the relative order of those leftovers.
Which brings us to Section 5, the pivot strategy.
This twist completely flips the script, because our previous, highly optimized one-pass solution relied entirely on perfectly matched pairs. It is completely useless here. We have to pivot. Think about it. If we try to use that brilliant pos index and neg index trick now, we are going to crash hard. Imagine having 5 positives and 1 negative. Your positive index is going to keep leaping by 2, 0, 2, 4, 6, 8. Meanwhile, your negative index just stalls out at 1. You will literally leave empty gaps in your array where negatives were supposed to go, and your positive pointer will inevitably jump straight out of bounds. The strictly alternating math is just broken.
So what's the play? A lot of folks freeze up right here, but the absolute smartest move is actually to swallow your pride and fall back to our modified brute force. Step 1, do the split. Iterate and separate the numbers into a positive list and a negative list. Step 2, figure out which list is smaller. We alternate elements into our answer array exactly up to the size of that smaller list. Step 3, whichever list is larger, we just iterate through its remaining leftovers and append them to the end. It's a fantastic reminder that sometimes your suboptimal safety net is literally the only framework robust enough to handle messy, unequal data.
Finally, Section 6, space and time complexity.
To wrap up the interview and prove we truly understand our own code, we've got to give the final scorecard. Let's break down time complexity first. Whether we're using that slick one pass for the first variety or our brute force fallback for the twist, the worst case scenario scales linearly with the size of the array. That gives us a solid big O of n time. Even in the second variety, where we iterate to separate, then iterate to alternate, and then iterate to append leftovers, mathematically it boils down to roughly big O of 2n in the worst case. And you know the rules of big O notation, we drop the constant, so it solidly remains O of n time.
As for space complexity, we're also sitting cleanly at big O of n. Why? Well, in both varieties, we are explicitly asked to create a completely new layout. We literally always need extra space, either to directly generate that final answer array in our optimal solution, or to temporarily hold our separated positive and negative buckets in the fallback solution. The space we require grows exactly in proportion to the number of elements, n.
Honestly, this problem is just a beautiful masterclass in algorithmic thinking. We started with this elegant, perfectly balanced scenario, engineered a hyper-efficient solution, and then watched it completely fall apart the second that guarantee of equality vanished. As you gear up for your next technical challenge, I want to leave you with this. How adaptable is your logic when the rules suddenly change? What other hidden assumptions in your favorite, highly optimized algorithms are just waiting to be completely broken by a slight twist in the constraints? Keep that in mind, and happy optimizing.